In this video, we present our work on privacy-preserving partial localization. My name is Marcel Gebhardt, and this project was joint work with Victor Larsen, Johannes Schönberger, and Mark Polleface. The main idea of this work is to divide the localization task into multiple under-constraint problems. To this end, we create secure parallel plane maps and distribute them to different servers. At query time, each server can only observe the partial constraints along its plane normal and therefore not obtain the user's full pose or location. The partial solutions can still be combined on the client side to obtain the full 6 degree of freedom pose. Our method requires a query structure with 3D points and corresponding descriptors. After feature matching, the points can be aligned with their corresponding map planes. This leaves 2 degrees of freedom in the position and 1 degree of freedom in the orientation. Intuitively, the location is restricted to a plane in 3D. Multiple queries with different map normal directions lead to intersecting constraints. The results can be merged, which leads to a single degree of freedom left in the location and a fully constrained orientation. By adding a third partial pose, we can finally also fully constrain the location. As an important detail, this also means that if other constraints are already known, for example, the position is restricted to the ground plane, already 2 servers are sufficient to obtain the necessary information. The partial pose constraint can be directly derived from standard point-to-point alignment. Here we try to find a rotation and translation that maps 2 sets of points onto each other. Extracting a single row of the system directly gives the partial constraints along the corresponding coordinate axis. Inversely, this also means that by choosing the plane normals along the coordinate axis, we can simply stack the partial results to obtain the full pose. However, with noise in the data, the 3 rows of the rotation matrix will usually not be perfectly orthogonal, and we need to project the matrix back to a proper rotation. For the minimal solver, we need 3 query points and their corresponding map plane offsets. We use the unit norm of the rotation matrix row as an additional constraint, but we cannot enforce the orthogonality between the rows directly in the solver. For map creation, we start from a normal point cloud. We split it into 3 disjoint clouds, choose the normal direction for each, and then lift the points to planes. We compare our method both to standard point-to-point alignment and to the privacy-preserving point-to-randomly oriented plane alignment as presented by Spatially and others. Here we use structure for motion to construct both the map and query. Our method generally performs slightly worse than the baseline, but comes with additional privacy benefits. Note that we optimize the RANSEC inlier thresholds for each method separately, which likely generates some noise, especially in the lowest error class. Additionally, we also evaluate the method using queries from an active depth sensor. In scenes with good correspondences, our method performs almost on par with the baselines. With few good features in the scene, the performance drops for all methods, but ours is much more affected than the baselines. This can partially be explained with our requirement of 3x3 inlier correspondences for the minimal solver. If you want to learn more about the project, please visit our poster session. All materials are also available on the paper website.